Naval Research Laboratory. He did his undergraduate studies at Berkeley. Then he moved to Caltech, so still in California, where he did his PhD. After that, he was a postdoctoral fellow at the Naval Research Laboratory. And after being there as a postdoc, he became a federal employee there, so a staff scientist there. And currently, he's the head of the high energy astrophysics in the application section. Now, as you will hear, he's also the PI of Strobex. And we will hear a lot from that mission today, I hope. Now, I should tell you that Paul is sitting in B442, and I circulated his visitor schedule earlier this week, or actually it was last week. So if you want to meet with him, please sign up on his schedule. So I don't want to waste any more time. Please.
Great. Thank you very much. All right. I hope the sound is okay.
Yep.
Sounds a little, move it down a little bit. All right. So yeah, I'm going to tell you about basically high throughput X-ray astronomy at two different scales. One is smaller and currently existing right now, and the other is larger, and it's the probe class study, Strobex, that we have been working on and just turned in the study report for. So first, NICER. NICER is a mission of opportunity, a relatively small mission, a $70 million total budget that's led by Keith Gendreau at Goddard Space Flight Center. We launched in June of 2017, and so we've kind of, it's an external payload attached to the space station, so we take advantage of all the resources of the space station, basically unlimited mass and power and data volume, at the expense of having to be human spaceflight rated and deal with giant things moving through your field of view and things like that. So there's pros and cons, but definitely a lot of pros, and making a very capable mission quite inexpensive by leveraging off someone else's $100 billion investment in the space station. We've just completed our initial 18-month primary mission, which was extended through the end of this fiscal year. And now we're going into our guest observer phase, where it's an open telescope for everyone to use. And we're in the senior review competition now to get funding for that for the next 3 years at least. It's very inexpensive as a mission of opportunity with a small staff. So we hope that we're optimistic that we'll be selected to continue. It's basically a 0.2 to 12 keV X-ray telescope. And in addition to its primary mission, which was sold to the NASA Science Mission Directorate to do astrophysics, of course, it was also partially funded by the NASA Space Technology Mission Directorate to do a demonstration of an applied engineering topic, which is using X-ray pulsars for spacecraft navigation. And this is the perfect instrument for demonstrating that capability, and that worked really well. I'm not going to talk about that, but if anyone's interested in the navigation aspects, I'm happy to talk about it either later or alone. All right, so what's the capability of this thing? It's as an inexpensive mission, how do you make a big impact? And one is that you give up on something. So we don't have any imaging. It's a light bucket. But in return for that, we can make a tremendously large collecting area. It's got about twice the collecting area of XMM Newton's PN camera, with extremely precise timing on every photon and CCD scale energy resolution, 85 eV at a kilovolt, 140 eV at the iron line. So you can get a lot in return for turning, making the mirrors much simpler, getting rid of the second bounce, so it's not a focusing optic, it's just a concentrating optic. And that concentration gives us low background. And the fact that it's divided up into multiple telescopes, there's 56 identical of these concentrator detector pairs, means that we really have no pileup, and we can handle a maximum rate of almost 40,000 counts per second, 3.5 crab, without degradation and losing data. And that's to be contrasted with some of the faint millisecond pulsars that we observed that are maybe 0.01 counts per second. So we observe sources over a tremendous dynamic range in brightness. So the science opportunities that are presented are, we can do fast timing and high throughput timing for the first time at low energies. If you are familiar with XTE, a previous timing mission, you really couldn't go below 2.5 keV or so. We extend that timing down to the soft band. We can see much fainter sources because of that concentrating in the low background. We see all sorts of new transients. It's been just a bonanza of transient discovery. The instrument capabilities are highly optimized for observing pulsars. That's why it's so good at neutron stars, thus the name Neutron Star Interior Composition Explorer. But it's very broadly capable, and there's been a tremendous amount of science on non-neutron star topics as well. So what does the spacecraft look like, or instrument look like? We're attached to the space station via this thing called the FRAM, the Flight Releasable Attachment Mechanism. That's a standard that's provided by NASA. Goddard used some high heritage components to build a 2-axis gimbal. It actually has one that deploys and then a 2-axis wrist that can point around anywhere on the sky that's visible. And then here you can see the X-ray optics on the front, 56 of them, and the detectors on the back, a star camera, electronics boxes, and there's sunshades and everything like that, so it can point anywhere at least 45 degrees away from the sun. But the whole sky is accessible within the constraints of the ISS, which has its own large moving solar panels and various things like that that you have to avoid. Okay. So the detectors, Keith Gendreau has been very aggressive at using very simple and inexpensive components. So these are commercial off-the-shelf AmpTech detectors that you can go and buy in a catalog. Really, they work really well, and they're really inexpensive, which is fantastic. The electronics that AmpTech had weren't up to the job that we needed, so MIT led the design of the focal plane modules, which incorporate these AmpTech detectors and some new electronics that read it out very fast that give us this ability to do 100 nanosecond time resolutions. Each detector is cooled, and so these detectors are simple, well proven, work incredibly well. They have all continued to, all 56 they're all, everyone that were working at launch are still working. Here's what it looks like when you integrate that many detectors together. You've got, this is the backplane, and you can see all the focal plane modules and all the harnesses. So the cabling is a big nightmare of spaghetti of cables, but that's what the back looks like, and it works really well. There were actually 4 detectors that failed during testing before launch. And it's, in most cases, it seems like it wasn't the detector that failed, but really the connection, the harness connection. So we launched with 52 working out of the 56 total. And to this day, they're all the ones that were working are still perfectly working. So that has been extremely successful. The optics are also kind of a triumph of simplicity. Most X-ray optics, as you well know, are like Walter 1 configurations where you have dual bounces and you get imaging over a large field of view, and that's great, but you pay that efficiency penalty twice for 2 reflections. Here, these are single shell aluminum foil mirrors. They're gold coated, and they're formed to a parabolic shape, not a conical approximation. And they have this Takashi Okajima at Goddard led this development. And they slide into these spiders that hold them in place, and they work really well. They're super light, very efficient. You get a tremendous amount of collecting area, but they only really focus properly for something that's right on axis. So as soon as you go off axis, coma goes all to hell, and so we don't have any imaging. It just the central part of the field of view is the detector with a 2 millimeter aperture, and we just count all the photons that get into that aperture. They were all built by hand at Goddard. There's 56 of them sitting on the table. These things can be easily mass-produced. The process was worked out and works really well. And so the technology has been fantastic. So the primary goals of NICER that were selected in the mission of opportunity were to do a range of neutron star science. And so in order to accomplish that science, we divided the science team into several groups that led different aspects of neutron star science. And then using whatever time is left, we have a group that does observatory science that covers any of the topics that weren't part of that main group. So light curve modeling is I'll show you some of the early results from that, which is trying to derive the equation of state of matter at supernuclear densities using modeling of the emission from the surface of millisecond pulsars. Bursts and accretion phenomena is led by DeepToe, which is looking at X-ray bursts and accretion phenomena and X-ray binaries. I lead one on pulsar searching, so all the kind of searching for new oscillations and pulsations comes from my group, as well as coordinating some with multi-wavelength observatories. Andrea Lohman does the high precision timing. This is the highest precision X-ray timing instrument that has ever been flown, 100 nanosecond time resolution, absolute to GPS for every single photon. That's unique. And so we are able to do long-term high precision timing, and I'll show a couple of results from that. Teru leads a group on magnetars and magnetospheres. And then finally, we have the observatory science and calibration. So that's just a bunch of words. These are the actual people. This is at one of the science meetings at MIT. So it's a relatively small group, but we've been really active doing all this level 1 science. So let me just give you a couple of quick intros to a couple of the science topics. I don't want to take too long. There's tons of science, but I'll just want to tell you the ones, especially the ones we get asked about a lot. So here's the idea. We don't understand what's going on at the core of neutron stars. The matter is at approximately twice the nuclear density, and there's a lot of new physics can be happening at those high densities. And so the best handle that you can get on that, or one of the best things, the simplest possible external measurable is to measure the radius of the neutron star. You can measure, we know many neutron star masses very precisely. We know very few neutron star radii and very imprecisely. So if you can make a precise measurement of the mass, that can tell you, you can directly calculate the radius from the equation of state, that is the relationship between pressure and density, and so the radius will tell you what the equation of state is. How do you get the radius? Well, we know that there are hot spots on the surface of the neutron stars. In the millisecond pulsars, that's typically caused by return currents from the magnetosphere heating a spot on the surface. So you have a hot spot on the neutron star. Here's what a hot spot on a star looks like if there were no gravity. So you can see the spot gets occulted, it goes away. The light curve looks something like this. When you turn on gravity, depending on the compactness of the star, you see something that looks more like this, where there's a number of effects, relativistic Doppler shifting, there's light bending, and that's why you can see around to the back of the star, so the spot is never completely occulted in this image. And so it changes the shape and the depth of the light curve, and also has spectral effects from the Doppler shift. So by fitting these pulse profiles from these rotating hotspots, you can make a measurement of the compactness and the radius of the neutron star. That's the idea. I'm not going into this in great detail because it would be a whole talk on its own, but at the head meeting, Anna Watts showed the first of our real parameter extractions. Let me say that this is very preliminary, so don't take the absolute numbers that we're getting for the radius as gospel just yet. There's a long process that has been gone through by the light curves working group. First of all, there's a number of different theoretical groups that worked out the details of the GR light curve modeling, that is making synthetic data, doing the ray tracing. They've actually found some inconsistencies between their groups. Now everybody agrees to 0.1% on what the shape of the pulse profile should look like for a given spot geometry on the surface. And then they're doing parameter extractions now by assuming a spot geometry on the surface and then extracting what the radius is from the observed data. So in this case, the data in 2 dimensions look like this, with pulse phase along the x-axis and pulse height, energy, along the y-axis. So you can see we have these 2-dimensional phase energy light curves. The model looks like this. We get good fits. But the radius that you extract from those good fits depends on how accurate your model of the thermal pattern on the surface of the star is. And so that's what's being worked on now. Anna's group has worked from very simple models where you have 2 diametrically opposed hotspots that are at the constant temperature to ones where they don't have to be at the diametrically opposed, they don't have the antipodal, and they can have different temperatures. And so as you work them up, you can say whether the Bayesian evidence favors moving to a more complex model or whether you've got enough model to explain your data. So this is sort of the second of the complexity levels of model. The first model was the spots that were antipodal. This is spots where there's dual temperatures. You can have like an annular spot, which is kind of what you might expect from heating. And for this particular set of constraints on the spot geometry, we derive this radius measurement here, which is about 8% accuracy. So we're getting down to the accuracy, the statistical power that we expected from these data, and we're doing this for several sources. This is on J0030, the first of the sources that we've been extracting. As we go, she's adding more complexity, and with her graduate student, we'll see what is the final preferred spot model. It comes down to really understanding what that temperature distribution on the surface of a star is. And so this is what the temperature distribution on the star looks like, and this is where I start to realize that we still need to think more about this, because most people would assume that something like a neutron star would have a dipolar, predominantly magnetic field, and that the spots would thus be basically in two different hemispheres of the star. In fact, the best fits in this model come out with the two spots both in the southern hemisphere. They're both in the same hemisphere. So there's something more complex about the geometry of these hotspots than we were expecting, and it could be that it's an offset dipole from the center. It could be that there's higher multipoles. So understanding what that distribution of temperatures on the surfaces is going to be critical. And I think they're kind of working it from a purely empirical point of view now, what temperature distribution fits the data. But I think there's room to go from the other direction and say, knowing what we know about pulsars and return currents and how we're heated, I've started to see calculations of what we should expect the temperature distribution to be and kind of inform things from that. So that work is continuing to go forward, and keep looking out for more results from that group. The other one I wanted to mention quickly was the precision X-ray pulsar timing. This is the first millisecond pulsar, B1937 plus 21. It's a 1.5 millisecond pulsar. The red here is the radio pulse profile, and the black here is the nicer pulse profile. This is a 1.5 millisecond period. So this narrow peak here is about 22 microseconds wide. It's an incredibly narrow feature in the X-ray, and we can time it incredibly precisely. So this is showing the TOA uncertainty as a function of exposure time. This takes all the different days that we've observed this source. We observe it frequently, multiple times per week. And you can see that it follows the expected uncertainty Poisson statistics, telling you that the uncertainty should scale with exposure time, and it does follow exactly both the theoretical expectation as well as the red line is simulated TOAs. We understand the data. It really is Poisson dominated. So now what we're doing is we're comparing the timing that we get, this precise timing in the X-ray, to the timing that's being done very precisely in the radio wave for NanoGrav, which is a pulsar timing array project trying to detect gravitational waves with pulsar timing. So we have over a decade of data on 1937 in the radio band, which are the colored points, and you can see it wanders about the solution. Some amount of that wandering is likely due to uncertainties in the propagation effects. Radio waves traveling through the interstellar medium are subject to both dispersion and scattering. It causes delays, and we try to correct that as best we can in NanoGrav and the radio, but it's always an imperfect process. In the X-rays, we are at infinite frequency. There are no propagation effects, so we know that anything that we see are intrinsic spin variations in the pulsar. And so we are not, our error bars are the black ones here. We have larger error bars of a few microseconds. We're not down to the 100 nanosecond level, but we do have that infinite frequency. And so we're trying to compare to see, do we see things change? Do we see things look in the same way in the radio band as we do in the X-ray band? And so the red points here are a measure of stability. This is a clock metric called sigma z that we're seeing as we integrate longer and longer. The stability measure goes down in the X-ray, which is this nicer data is red. The other data is the NanoGrav data is the blue. It turns up as we see the red noise process start to keep that from integrating, the stability measure from integrating down and down and down. And so what we're interested to see is, as the nicer mission goes on, does the X-ray continue down, or does it turn up at the same time scale, or what? And so we're keeping an eye on that. It's kind of a long-term project because it has to compete with the 10 years of data from the radio and the long time scale of the red noise. So in addition to those primary neutron star topics, NICER has been, as I said, this incredible general purpose observatory. And because we're in contact with the space station basically 80% of the time, and our PI does all the scheduling, we just tell him when a black hole goes off or some flare star happens or there's some interesting coordinated observing opportunity with another satellite, and he can quickly reschedule. And so we have observed a huge range of sources over the duration of the mission. And Jack Steiner here, a recently joined CFA here, made this plot, and it's amazing. It shows the dynamic range, as I mentioned, of this is just counts per second for all the different OBS IDs that NICER has made over the year and a half. And he's tracked a few of the bright sources. Some of the crab is here nice and steady at 1 crab, thankfully. And black holes go up and down, flare and reflare, and we see them over huge dynamic ranges up here, well over a crab, down here to millicrabs, sub-millicrabs. So it's been just amazing that we're able to track. And you can see, because we slew so fast, we can revisit sources very frequently. So you see the density of these monitoring observations that we can get. That's something special for a mission like NICER, or a rapidly slewing mission like NICER, that other missions that take a much longer time to plan and slew aren't able to replicate that kind of rapid revisit rates. So there's many, many papers. I'm obviously not going to read these. There's a huge range of papers that are coming out on a wide variety of topics. We were happy to have the cover of Nature from Erin Kara's really nice results on the contraction of the corona in a black hole transient that she measured with reverberation mapping. And so that's been a very powerful technique. And I think that we're seeing that kind of spectral timing work, reverberation mapping, really showing up to become very powerful as we have these high throughput observatories. And obviously I'll get to that later as I talk about the next high throughput observatory. But to let all of you know, as we've passed the beginning part of the mission where most of it was pre-planned before launch, now the time is rapidly becoming dominated by guest observer time and TOO time. So I encourage you to go. You can go on the web and request a TOO. There's a form. It's simple. You'll likely get it unless it's something that can't be done. Take advantage of this resource. It can get on a source that your favorite source very quickly and do impressively good science. Cycle 1 GEO program is just beginning. They've all been selected and observations have already begun. And the Cycle 2 will happen next year, senior review willing. So this is something that most people don't get to see, which is their own experiment in space working on high-definition television. Mostly once you launch your Chandra or whatever, you don't get to see it again. This is amazing, being on space station. So you can see it when it turns around behind. You can see the thermal radiators. You can see the star tracker and the 56 concentrating optics and their sun shields, and then all sorts of other stuff happening. You can imagine we have a three-dimensional model of all these things swinging in the way so that we don't accidentally point at the solar panels or something that blocks our view. And of course, it happens, mistakes get made, and you're like, what happened? My source went away. And then solar panel, sorry. So that's the end of what I was going to say on NICER. If anyone has a question on NICER now that they want to ask, I'm happy to say that before I move on to the next part. Yeah?
So you mentioned about the light curve modeling.
Yeah.
So the one which you showed was for, I think, isolated neutron stars?
That's J0030, which is indeed isolated millisecond pulsar, yes.
So can you also do that for the accretion powered pulsar and maybe differentiate between a fan beam or a pencil beam pattern of radiation?
You can. So accretion-powered millisecond pulsars, we have done a lot of work on. We've seen a lot. It's not. It's much harder to do the light curve modeling to get equation of state constraints from that because we don't understand that their pulse profiles are much more complicated. I mean, they're not that complicated generally, but they change shape as the outbursts progress, and so we don't have a simple model to use the accretion-powered millisecond pulsars to extract the radius. So the places where you have simple models are from the hotspots on the surface of an isolated star is not accreting, and from the burst oscillations, where in a bursting neutron star, if you have an ignition at a point, you should at least for a while have a very simple situation with basically a point light or a very small spot on the surface, that's hard to do because that only lasts for a few seconds. And so that's not accessible to NICER because in a burst oscillation, we don't get enough photons in those few seconds to do that precise modeling. That will change in the next half of my talk. So, yep.
So somebody showed the X-ray as well as radio light curves for a certain source.
Yes.
And it looked like they were offset by the
Yes.
Did that have to do with like a calibration error, or is it physical, and do you understand it?
Yeah, so it's definitely physical. It's definitely not a calibration error. There's a range of different offsets that you see between X-ray and gamma ray or high energy emission and the radio emission. And it's because of either different locations where it's emitted. So there's two classes of pulsars, basically. One's where the emission is basically aligned, where you think that it's coming from roughly the same part of the magnetosphere, and one's where it's not aligned. And so in a lot of cases, like the Fermi emission will come from further out in the magnetosphere near the light cylinder, whereas the X-ray emission that we're seeing, and there's different classes. So there's the ones that are from hot spots on the surface, and there's ones for up in the magnetosphere. That particular pulsar I showed was 1937, which is a very non-thermal pulsar. So the emission that we're seeing in X-ray and radio are both coming from the outer magnetosphere, not from the star. It's from the surface of the star. So what you're seeing is different delays as it's propagating out from slightly different altitudes or spots in the magnetosphere. So they have slightly different paths to travel to get out. Yeah, Jack.
So Paul, just quickly also on 1937, the fact that you have such different asymmetry between the secondary and the primary maxima in X-ray and radio, what is that telling you about the geometry, just given the X-ray to radio difference?
So I don't really know. We're seeing two different poles of the neutron star. So yeah, there it is, the 1937 light curve, and indeed they're both the radio and X-ray are brighter on one side and the other. So I think one pole is just passing closer to your line of sight than the other would be my interpretation. But I don't exactly know how much more physically I can tell you about that personally.
How often do you have to button up, and have you had to shut down entirely?
We have. Mostly it has been not a problem. We were worried that we might have to nod down and close up shop whenever they, flush their toilet or whatever, but that has not been a problem. If an EVA is happening close to us, for safety reasons, we have to make sure that we're shut down. But for the most part, we've had much better observing efficiency than we had expected. I forget what the number was. I think we were expecting, I don't remember, but we're getting many percent. It was like a large fraction more efficient observing than we expected, and that led to a lot more time available for TOOs and DDTs and other kinds of science. We see all kinds of crazy things on the space station. When it had a leak, there was a Russian astronaut came outside and had a knife and jabbing through the MLI to try to locate the hole in the space station, and the pieces we can see, fluttering pieces of MLI flying by and reflected. I mean, there's some crazy stuff goes on up there. So, yeah. All right, anyone else? All right, so that's the current time, and as you all know, NASA is preparing for the next decadal survey. There's actually a telecon on it this afternoon where hopefully they will announce the members of the panel. And as part of that, they funded a set of 10 or so studies of what are called probe class missions. That is, missions that are larger than explorers, larger than a couple of 100 million, but less than the very large missions, than the very large four huge missions that would allow NASA to have some programmatic flexibility and be able to feed in some medium-scale missions when they weren't able to, say, start the next giant thing, or they had some free energy in the budget. And so, yeah, so so I was, all right, what else I want to say about it politically? But anyway, one of those proposals was StrobeX, which I was the PI of, but hardly the only person on. We have a very large group of people working on this mission concept. This is our steering committee, the people that were most closely involved in doing the study and writing the study report, which was just funded. We had to submit a 50-page study report from this. But there's also a much larger group of about 150 people on our science working group that have contributed all sorts of science ideas and text to our science case. And so very broad community interest in it. And so StrobeX stands for Spectroscopic Time Resolving Observatory for Broadband Energy X-rays. But what we do is timing and spectroscopy on a large range of dynamical timescales. So now, why are we pushing for a flexible high throughput X-ray observatory? Well, as you probably all know, the X-ray high energy sky in general is extremely dynamic. There basically are no steady point sources. Everything is variable. And so you need to be aware of what's going on in the sky, and you need to catch the right source at the right time to make those big science advances. And we had 16 years of this with XTE. This is a timeline of some of the transient seen over a couple of years that Ron Remillard made from the XTE All-Sky Monitor data. And you can see this, just the huge range of sources and flaring periods and behaviors that you get from these sources. And so you have to have an observatory that can take advantage of that. And this is a critical capability in the era of time domain astronomy and multi-messenger, where we have many more wide field instruments like LSST and SKA and CHIME, and we have a huge host of things that are working and LIGO and Virgo working in the time domain and finding flaring and variable sources. But also timing, X-ray timing and precise timing and high throughput timing is sensitive to source geometries. It allows you to measure these time delays between features or lags between spectral bands. And so you're sensitive to geometry in a way that's very complementary to what you get from spectroscopy and high resolution imaging. So really, all three of those capabilities are needed going forward to understand all these broad range of sources. And it takes large area, collecting area, but also very low dead time in order to access those shortest timescales of variability in sources. Crucially, you need both the soft and the hard X-ray band in order to get a full picture of the continuum spectral shape and the relationship between thermal components like disks and surfaces and non-thermal components like reflection and Comptonization. You can't have the whole picture until you get very broadband coverage. And it turns out that this decade, as you see already with NICER, technology is already available to make that order of magnitude leap over previous generations. And that's the change from the old days of gas proportional counters and huge heavy collimators to modern silicon detectors, mainly silicon drift detectors, and very thin collimators that make things for the same rough mass much, much tinier volume and much larger collecting area. So another thing I saw at the HEAD meeting was Daryl Haggard likes to give a lot of talks about time domain astronomy, and I grabbed this slide from her. Thank you to Daryl. This is what she said. This is totally unprompted by me, by the way, what the high energy astrophysics needs in time domain in the 2020s. She talks about, for discovering and monitoring, you need an all-sky monitor to see these gravitational wave counterparts, supernova shock breakouts, tidal disruption events with at least daily cadence. You need rapid response, being able to slew in timescales of less than hours, to follow up on these sources with high availability. And you need high time resolution with sub-millisecond timing to get at these very fast phenomena, and QPOs and strong gravity phenomena, and you need to do that with high sensitivity. And I was really happy when I saw this because StrobeX, our concept, meets all of these in many cases by more than an order of magnitude. So that's hugely important for us as a driver. So this is what that instrument looks like. This is StrobeX. The central portion here is dominated by what you can think of basically as a super NICER. It's a soft it really is just a scaled up version of NICER. So a lot of collecting area in the soft band and the 0.2 to 12 keV band. These wings out here are the large area detector. That is our collimated harder X-ray detector that goes from 2 to 30 keV that gets you that Compton hump and the harder phenomena and a tremendous amount of much more collecting area as a collimated rather than focusing instrument. And then you can see our spacecraft and solar panels. And at the top here are the wide field monitor cameras that give us that view of the sky, wide field all the sky. So the two instruments are the orange and the blue, this effective area curve versus energy. And you can see, and the sum is in black. And you can see that we're well above any, an order of magnitude or more above any current instrument, and even well above proposed missions like Athena, which obviously is very different in being a focusing and high spectral resolution mission. But critically, if you're doing studies in the iron line region, Athena might be down at around 1/4 of a square meter of collecting area, and we're at over 5 square meters of collecting area. So really a tremendous amount of collecting area if you're doing things, science around the iron line. So we combine this strength of NICER and LOFT, which was the European version that had where we got these instruments from. Everything is already at high TRL, and very importantly, this very highly modular design. These are 4 identical quadrants. That gives you 1 layer of modularity, and then all of these individual modules and concentrators give you another layer of modularity. So that modularity we take advantage of massively in our design and risk assessment and cost assessment. So the concentrators are, here's the NICER ones that you just saw flying. Here's what the XRCA concentrators would look like, or would look like. That's about 3 times the focal length, going from 1 meter to 3 meters. That gives us more collecting area per detector so that the background per unit area is actually lower. Otherwise, it's basically the same. And so it's really just a scaled up NICER. I don't need to spend too long on that. The large area detector relies on a technology developed in Europe for ground-based particle accelerator experiments. These are large area. This is 10 by 7 centimeter silicon drift detectors that have strips down them. Those give us pretty good energy resolution, 200 to 500 EV, but have this very large collecting area up to 30 keV. They're thick. And so that's what gives us this capability to see the non-thermal emission, the Compton hump, and really a lot of the collecting area at the iron line region. So that technology has been well developed for LOFTs during the LOFT study in Europe. We take those same detectors and just make them with a finer strip pitch, and that gives us imaging capability in 1 dimension, basically. And so we build our all-sky monitor cameras out of that. They're coated aperture mask cameras that are basically they're 1.5 dimensional because you have a little bit of resolution along the strip direction, but most of it is in just which strip is hit. And so we have each pair of cameras has strips as coated masks that are crossed in 2 different directions to give you X and Y so that you can localize sources to have order an arc minute. It's continuous viewing. Many of you are familiar with all-sky monitors like MAXI or ASM that scan the sky, and every once in a while you get a few seconds on your target. So you get a very broken up light curve. These ones are wide field imaging cameras, and so they see things all the time. And so you can see phenomena down at short time scales, milliseconds and all the way up to years. So you get that huge dynamic range and timescales that's not broken up. So you can even see QPOs in SCO X1 all the time as it's in your field of view and things like that. You can do a tremendous more, and you have that huge grasp of the sky, which lets you find rare events. So it's really a game-changing development to have a wide field continuous viewing, not scanning sky monitor. And it has onboard processing built into it that can trigger autonomous repoints to get the big instruments onto a flaring source very quickly, and that can be super exciting for things like GRB counterparts, or for like looking for millisecond magnetars, or superbursts would be phenomenal to do neutron star seismology by getting onto a superburst. There's a tremendous amount of science you can do, and I'll just touch on a couple of things. One of the things that drives our mission is black holes on all mass scales, from stellar mass black holes to supermassive black holes, probing the spin distribution of black holes, which touches on their formation mechanisms and evolution. One of the great things is that we have 3 different techniques to access the spin of a black hole. We can look at high-frequency QPOs, we can look at the continuum spectral fitting, and we can look at reflection fitting. Those are all accessible to Strobex, and that gives us multiple views at something to let us understand the systematic errors and try to constrain that and know that more confidence that modeling errors or uncertainties in the physics aren't polluting our measurements. We can do incredible reverberation mapping with this high sensitivity and high throughput. Both stellar mass black holes and AGN. This plot Aaron Kara made that shows the Strobex lag uncertainty as a function of energy, and it's really fantastic all the way through the X-ray band. The kind of a lag measurement that she was able to do in 100 kiloseconds with XMM can be done in 100 seconds with Strobex. So that will be a really powerful, the reverberation mapping gives you this geometry because you see the time delays between the emission from the corona and the relativistic reflection. And those time delays tell you about the geometry of the system in a way that you can't access in other ways. So we also, a tremendous amount of other science, variable disk winds, QPOs, the physics of state changes in accreting systems, the disk jet connection, a lot more. For neutron stars, I showed you what NICER is doing. It's going to do that kind of measurement for 1 or 2 neutron stars. Strobex will be able to access 15 or 20 millisecond pulsars in that way, which will expand expand the range of masses over which we're probing that, and that's very important to really understand the equation of state. Is you don't just want to measure the radius at one mass, you want to measure the radius as a function of mass, and we can do that. And again, unlike NICER, which can only access this by one technique, which is the thermal surface emission, we'll be able to access those burst oscillations I was talking about, the very early onset of a X-ray burst, and we'll can try to use the accretion-powered pulsars, and those multiple techniques and multiple numbers of systems will help us mitigate systematic errors. So there'll be a lot of work on neutron stars, of course, but also in the time domain, we have this huge topic of all sorts of rapid and extreme explosions, gamma ray bursts, gravitational wave counterparts for LISA and LIGO, TDEs, shock breakouts, bursts and superbursts, and that's really enabled by this wide field monitor features, the arc minute localization that we have that allows you to follow up with a single pointing of a typical optical telescope with IFU. Large instantaneous field of view, that's I've mentioned already, that allows us access to rare events. If you're surveying a third of the sky all the time, you can see extremely rare events. The autonomous repointing will allow us, and the very fast response to ground TOOs will allow us to get on sources when we need to make the measurements. And that good spectral resolution means that you're not just getting a couple of bands out of your sky monitor, you're actually getting spectra from sources out of your sky monitor. And we do telemeter all of the continuous event data, so we can do full timing on even the sky monitor data. So as part of our study, as I said, we enlisted over 150 people to think about the kind of science that you could do with this mission, and it really turns out to be this incredibly broad portfolio. These are some of the topics that are covered in our 50-page report. I encourage you to take a look at it if there's any science that you're interested in. Look up the report. They're all posted on arXiv, and NASA posted all of the probe study reports on their Preparing for the Decadal Survey website. It's really a huge range of science that we'll be able to do. So as part of the study, what you do is they fund you to go to the design labs, either the ones at Goddard or the ones at JPL, to flesh out your instrument and mission concept. So in November of 2017, we went to the instrument design lab at Goddard. They designed this detailed instrument design based on the pieces that we gave them, which were the fundamental subparts of the instrument. But they worked out this optical bench, which is a composite optical bench that's really helped us reduce mass and be stiff and avoid thermal distortions as we point to different regions of the sky. They worked out the deployment mechanism for these panels, so they launch closed and then are deployed. There's no concerns with that. That's very straightforward because these have a 1 degree field of view collimator. We don't have to point to subarc second levels or anything like that. So it's straightforward to deploy and put those out. And they did a detailed cost model for all the instruments. And there we are working in the IDL. Then we went to the Mission Design Lab in April of 2018, and they took that instrument concept and built a whole spacecraft and mission around it. They ended up moving the wide field monitor from where it was during the IDL to the top here. That alleviated the need to have a sun shield because of the way you can keep you have freedom of one axis around rotating around the field of view axis, so you can keep that guy in the shade, which is where he likes to be. And one thing I was really worried about was I kept selling this mission as being able to access the sky very quickly and slew very quickly, but it's the size of a school bus. Would I be able to slew as quick as I wanted to? And in fact, current high TRL control moment gyros are able to slew us at 15 degrees a minute. So that's a fantastic capability that we'll be using to be able to point quickly between sources and do autonomous repoints to triggers on board. TDRIS gives us the bandwidth we need to telemeter all those events. We don't have to downsample in spectra or time resolution. We have continuous access with the TDRIS S-band multi-access, so we can do TOO commanding. And then the Mission Design Lab takes all those things, wraps them up into a big cost estimate, and we do actually fit well within the probe class cost budget. I'll show you that in a second. Oh, here it is. So the cost estimate had several rules that all the probe classes had to follow. One, that these are Class B missions, which is substantially more stringent than the Class D mission that NICER is. That means you have to have dual string, you can't have single point failures and various things like that. All of us had a Phase A beginning in October 2023, which is sort of the first time you can imagine starting a mission like this if it was recommended by the Decadal Survey. And that gets us, with our development schedule, to a launch in about 2031. So putting that together with the estimates they did, plus these wraps that they traditionally include for things like project management, which you don't cost out line by line, you give it a percentage of the total budget. We all add up with 25% reserves on everything which is required to $880 million, which gives us more than 10% margin under the $1 billion cost cap. And it's very important that this includes only NASA funding. We're assuming completely conservatively that NASA is paying for absolutely everything on this. That's incredibly unlikely to be true in the end because a lot of this technology we developed with our international partners, very, very likely they would provide an instrument or provide the detectors free of charge, in-kind contributions to the mission, and that would reduce NASA's cost. So I think we would expect, in fact, to be considerably less than that. So StrobeX is got huge collecting area, fast timing, good spectral resolution, and it will address a range of fundamental questions in accretion, dense matter, black hole formation, evolution, and a lot more. It's based on existing technologies and high TRL designs with, that we have. So we have a lot of confidence in our cost estimates, I would say, and this highly modular design is really important for keeping the cost down, making an easy integration and test flow that is efficient and keeps our costs under control and our risk low, so that we can lose half a dozen of our concentrators or whatever, and it doesn't really bother. It takes down a little bit of the effective area, but doesn't keep us from doing our mission. And so I think StrobeX is going to serve this large community in the decade of time domain and multi-messenger astronomy with capabilities that are really complementary to the work that's being done on very high spectral and very high spatial resolution X-ray missions. And so I think we need all of those. And so keep up with us by following us on Twitter or Facebook. And we have a website. And anyone that stops by and sees me can have a sticker as well. So thank you very much.
Thank you very much.
Sure.
So I'm guessing that it's now time for questions about StrobeX, right?
Yep. Yeah.
So how does the effective area of StrobeX compare to HXMT and AstroSat?
So I don't know HXMT off the top of my head. for Astrosat LAX-PC is a lot like the XTE PCA, but it's high pressure xenon, so it goes out to higher energies. I think it's about 5,000 or 6,000 square centimeters. So 1/10. LAX-PC is 1/10 of StrobeX.
Oh, okay.
Yeah. And LAX-PC, I believe, lost one of their detectors. So I think it's a little bit less. I'm not sure the current effective area.
There's a lot in common with love. Have you had any discussions about merging data together?
Oh, that is what this is. So what happened was I proposed a timing mission to Astro 2010, and they were proposing LOFT at about that time. And we didn't go forward in the US at that time, and so we joined with LOFT. And we pursued LOFT in Europe for the M3 call, and we went through the assessment phase study with LOFT. And then when LOFT didn't get selected, an exoplanet mission was selected, then we came back across the Atlantic. And so the LOFT technology is the wide field monitor and the large area detector. But when it came back, we had just gone through this work with NICER, and so we realized that we had the capability to make a much more powerful mission than LOFT by having the soft and the hard. So the super NICER plus LOFT together, and that's what makes StrobeX. So Marco Ferrocci is the PI of LOFT, or was the PI of LOFT, because LOFT doesn't exist anymore, and he is intimately involved, was in all of the studies and worked on all of this with us. So yes, our European partners are very important.
Okay.
Downside of being very modular is it's very easy to descope you. So I would just wonder,
that has pros and cons, yes.
how would the cost go with the scaling of the number of modules? If you cut it in half, would it be half the cost? No, clearly. But
Yeah, so we didn't, this is a very limited study. We didn't get to do that kind of parametric change. I think there are going to be a few breakpoints. Like we have these 4 quadrants. If you cut it down by 2, it would cut the cost by a large factor, but you'd lose half the effective area. You could also just shrink everything, keep the quadrants, but shrink it down to a smaller number. There is cost saving to be had with that because some of our manufacturing and assembly and integration and test schedule is dominated by the large number of things that have to be built and tested. And so if you shorten your schedule, you shorten your cost. So there would be room to descope if that was viewed necessary. We could easily descope 25% and save a lot of money. Yeah.
Those Amtech STDs on NICER have a ton of flight heritage. I think there are a couple on Mars.
Yeah.
But the wide area detectors from the European partners, do they have any flight heritage? What's their
No. They don't have any flight heritage. They have been used for years in this, I'll get the name wrong, I think it's called D4 experiment in LHC. So they've been in extremely high radiation environments and ground-based particle accelerators, but we have not flown them yet. And so one of the things we would like to do is develop those into a package that we could test up to TRL6. And so if you're on the APRA review panel, I recommend approving my APRA to do the technology development that we need, which is basically to build an ASIC that's ready for this use. Yeah.
So there should be some systematics in the methods that you highlighted.
Yeah.
Examples could be when you do reverberation mapping, because of geometry or something that should be systematic. And if you systematically with that, you can be in a regime where you can measure time delays by time lags by 100 times better than XMM, but it doesn't mean that she's tracking 100 times more. So have you guys looked at whether your systematics limited at this drawback sensitivity already?
So it varies a lot on which science topic and which source you're looking at, but yes, so systematics are absolutely critical. When you have this much collecting area, photon statistics become negligible in many cases, and so systematics are critically important. For a lot of things like time lags and stuff, there's minimal systematics because we know the times of the photons precisely, and if there are systematics in interpreting the source, one way of approaching that is to observe more sources. So if you currently only had a small number of sources available, accessible to do reverberation mapping. If you extend that by another factor of 10, you've got a lot more sources, more chance to understand the systematics in the modeling. If you're looking at systematics in collecting area or spectral measurements, that's really important. And we realized that, and we have a few people on our group that really harped on that, in particular Mike Novak. And so Mike's been leading a subgroup of our study team in thinking about systematics and pushing both software approaches to it and thinking about what kind of hardware changes you would make, and we're kind of learning from NICER, what would you have done differently to, maybe there's small, inexpensive changes you can make to help, deal with some of those systematic errors. But for all missions, understanding your total collecting area perfectly is always hard, and so there's some things that we're not going to be able to do, but a lot of things where you're doing comparisons between bands and things like that aren't as affected by those kinds of systematics.
Yes, last question.
You were talking about doing follow-ups to gravitational wave detections. Can you do the opposite? Do you have candidates where you have like a pulsar binary or a black hole binary, and you know from the oscillations of their light curves that they are heading towards a merger?
I think we do see sources that are going to merge, but it's in hundreds of millions of years. But what we will, where we will have that is in like ultra-compact binaries, which will be LISA verification binaries. So we will be able to study binaries that will be visible to LISA and will be in the same epoch as LISA. So I think there's, in terms of the same source, there's a lot of commonality more with LISA. With LIGO, you're not going to know about the source in advance, and they won't have an EM counterpart in advance for most of them. Except for so I should say, we're so biased by what LIGO has seen so far. LIGO's going to find a lot more types of sources as it gets more sensitive. And one thing that we will definitely contribute to is looking for continuous wave, gravitational waves from either accreting millisecond pulsars or from normal rotation-powered pulsars. And so providing the ephemerides, understanding the periodicities that let you fold coherently the LIGO data, we're already doing that, and more sources are getting down below into scientifically interesting levels, and that will continue as they get more sensitive, and we start to be able to, and we get more sensitive, and we can find those. If we could find the pulse period in time, say SCOAX1, that would be very, very, very powerful for LIGO.
Okay. That's thankful.
All right, thank you.
I just want to introduce myself. My name is Joseph Hall.
Nice to meet you.
I'm working with Josh Ringley there.
Oh, yeah.
Yes. So I'd like to...
Hey, Josh. Good to see you. No worries.
Student thesis defense.
Oh, God.
That was Friday. I was chairing the committee, and it's